Good morning, everyone, once again. So, yesterday we started looking at the subject of continuity. So we had this definition 4.1, which was our definition of continuity. So we had our function being continuous at a point in its domain if the limit as x approaches a of f of x, if that is equal to the value that the function takes at a itself. It has a nice behavior of the function. But so far, this notion of limiting values of functions, we have only just talked about that in terms of as x gets closer and closer to a, the value f of x gets closer and closer to f. So with our limiting process defined using this kind of closer and closer to. And there's nothing incorrect about talking about explaining things like that, but it's only good as far as it goes. It's not technical or precise enough, formal enough to allow you to build rigorous arguments, okay? But you can't keep track of the various rates of convergence. If everything that converges is just described as well, it gets closer and closer to the limit. Well, if you're building and combining the convergence of multiple things with each other and tracking their combined effects, if everything is just described as well, this gets closer and closer to that, and this gets closer and closer to the other thing, and they could be doing this in a wide variety of very different rates. And so to keep track of the combined effect of everything, you need a better, clearer definition. Okay? So we would like to prove theorems 4.3 and 4.4, which are about the important function operations. And just remind ourselves what the important function operations are. They are basically addition of functions, multiplication of functions, taking quotients of functions, and doing compositions of functions. So these are defined, how do you create a new function out of two functions by adding them? Well, this is simply the function that any particular argument x, you just add the corresponding on it. So in order to define each of these new functions, you have to say what their values are. You can supply a definition to this thing on the left, and you'll have defined that new function in the first paragraph. The product function is just exactly the function that's the product of the individual values. Similarly for the quotient function, quotient of the individual values, and the composition function f after g is f applied to g applied to x. Okay, so those ways of defining new functions we're familiar with. Looked at those in the previous chapter on functions. But we want to prove theorems 4.3 and 4.4, which say, so it's kind of continuing this sentence, we want to prove these theorems about these important function operations, which say that if f and g are continuous, then so are each of these. So are each of these new functions. That's what we would like to do. So we then know that if we have a base collection of a group of functions, and there, anybody happen to lose a pound? You lost a pound, didn't collect it there. Stop thinking about pounds. What was I saying? Yeah, we'd like to know, and it's good that this concept of continuity that we've introduced, which is going to be fundamental and underlying the concept of the derivative that we're going to get onto, it's important to know that it interacts well with these ways of combining functions. Because once we have a collection of base kind of standard functions, we'll be able to combine them in all these different ways and know, we'll always be safe in the knowledge that the functions we're talking about are continuous functions. But in order to do this, we need a formal definition of convergence. Rigorous definition of convergence, of continuity. And it looks quite like the definition of convergence for sequences. So recall the def of convergence for sequences. Okay, so everybody knows this. A sequence xn converges to x as n goes to infinity if. So how did the definition work? Just remind ourselves, if for every epsilon existed an n such that n bigger than or equal to n implies that the absolute value of xn minus x is less than x. For every measure of closeness, epsilon is a measure of closeness of xn to x, and that last inequality there. For every measure of closeness, you can find a point in the sequence, this capital N, beyond which the sequence elements are always at least that close to the limit. That's our formal way of saying xn is getting closer and closer to x as n gets larger. So now we want to imitate this for continuity. Which remember says the limit as x approaches a of f of x is equal to f of a. That's our informal definition of continuity. So we want to just kind of translate this concept and these ideas and principles about sequence convergence into the kind of continuous domain or the appropriate context for a function of a real variable. Okay. So this brings us to definition 4.2. Some bits of it you will recognize from the definition of convergence for sequences, namely the role played by epsilon. But see, we're no longer talking about a sequence with an index n, so those bits are going to vary. So we say this is how the definition goes. So we'll just roll out the definition and then we'll look at the various bits of it closely and we'll explain it. So we say f is continuous. F is continuous at the point A in its domain if for every epsilon greater than 0, and epsilon greater than 0 is a measure of closeness. It's going to be our measure of closeness for the function values f of x to be close to the function value f of a. So epsilon is still playing the same kind of role, but I'm going to put more in the start of this line as well. But what's the kind of corresponding thing that the role of the capital N for sequences there? Well, for every epsilon greater than 0, it's going to be that there exists some delta bigger than 0. These are the numbers that are characters that are customarily used. So some delta, the Greek letter delta greater than 0, such that x is that close to a, that's going to imply that f of x is that close to f of x. So for every epsilon bigger than 0, there exists a delta greater than 0, such that, and delta is a similarly a degree of closeness, but it's for the argument of the function. I'm saying if the argument is this close to this limiting argument a, then the f of x values will be that close to the limiting value f. But the order in which these two parameters appear is important. So in symbols, in symbolic form, purely symbolic form, this becomes for all epsilon bigger than 0, there exists a delta bigger than 0, such that x minus a less than delta implies absolute value of f of x minus f of a less than epsilon. There's a diagram there that helps explain it. I'm going to repeat it because it can sometimes help to see the diagram being formed dynamically, how we draw the various bits and what order we draw the various bits of the elements of the picture. So, like, we're talking about a continuous function, so to speak. So a nice kind of rudely changing curve. Okay? So there's a point A in the domain. Here's the point in the graph. So coming across here, let's say at that level there is the value f of a, height of the graph at that point. So what we're meaning when we say this is continuous is for every epsilon. So this means somebody declares a measure of closeness around the value f of a. Somebody says, I want to see the function values be at least, or be at most, the distance epsilon away from the value f of a. So if, whenever somebody presents an epsilon bigger than 0, if we can always find some delta, so this would be a plus delta, a minus delta, we can always find a delta bigger than 0, and delta is a measure of closeness to a, such that for every x value here, every x value in this interval, the value f of x will always be inside this interval over here. We can check that that is indeed the case. For any x value in this interval has, well, we're talking about these points in the graph, so we kind of bring these to the extent of these horizontally across. And yeah, you see, for this interval here, this is the range of values we see. Color them both in red. Yeah? So somebody declares a value of epsilon. If for that value of epsilon, we can always, no matter what it is, we can always find a delta, such that for every x inside that interval, the corresponding f of x value, which I've roughly indicated the extent of them over there, if that always lies inside the epsilon interval, then the function is going to be continued. This choice can always be done. For any epsilon, there exists a delta. So if somebody insisted on a much smaller epsilon, if somebody said, well, I want things to be much closer to f of a, so they tightened the radius epsilon down to something extremely close to f of a, well, we would probably have to decrease the delta as well. We would have to insist that the arguments x were even closer to a. But because the function is continuous like this, no matter how small the epsilon is declared to be, we will always be able to find a corresponding delta so that the delta interval gets mapped by f to inside the epsilon. So it's continuous if, no matter what, epsilon bigger than 0 declared, we can always find the delta bigger than 0 so that f maps this interval, a minus delta to a plus delta, that maps that inside the interval f of a minus delta epsilon to f of a plus epsilon. Okay. One way, another slightly different way of articulating the definition. So it seems to be just a little bit more, I mean, it's kind of equivalent in difficulty or you know, to understand it as the definition of convergence for sequences, but you're quite familiar with that now. So it's a little bit new, but you understand it in very similar ways. Okay? So the role of this delta is now taking the place of the capital N in the definition of convergence of sequences. So this picture illustrates it here. Let's draw another picture to illustrate non-continuous behavior. Illustrating non-continuous behavior. And show that the definition breaks down. So illustrating non-continuous behavior to show definition does not hold. That's important to see as well. When you meet new definitions and concepts in mathematics, you always try and understand them from the kind of in the positive sense and the negative sense. But if you define a new concept, you have to be able to kind of recognize and understand things of that nature, but also equally well be able to recognize and understand things that do not have that nature. Yeah. Then you've got a kind of 360-degree understanding of the concept. Okay? As well as being able to appreciate how the definition works for continuous functions, we'd also like to see how it fails for non-continuous. That gives you insight into how everything fits together as well. So let's start by just sketching a function that is very clearly not continuous at this point A. Okay? It's one of these functions that makes an instantaneous jump. Okay? So along here, it's happily changing its values in a well-behaved, smooth, continuous way, but something weird happens here, and it immediately jumps up to this graph, and then continues to behave well. So this is non-continuous. So this is a jump at A. Now, there's some value of f of A declared. What are we going to make it? Let's just suppose f of A is defined to be this value here. So the function follows the graph either side of A, and at A itself, the function is defined to be that. I'll just show some value. And here's a value of epsilon. Okay. There's a value of epsilon. Distance here is epsilon distance. Now, does there exist a delta that satisfies the definition? What's the delta have to satisfy? The delta has to satisfy this. Some delta is supposed to exist for every epsilon. So there's an epsilon. does there exist a delta such that whenever x is distance from x and a is less than delta, that implies the distance from f of x to f of a is less than x? Well, if you try and construct one, let's make delta really, let's make delta quite small. So we're talking about this extent of values either side of a. Yeah, I mean, the highest we get, bring this up to here, and look at values to the right of a, yeah, the highest we go is maybe that extent there. But you see, this integral delta goes either side of. So there, this little red stroke I've just drawn there is just representing the right-hand side of the interval. But the interval always extends slightly to the left of it. Okay. But see there, the values are being picked up here. Okay. So the extent of values there, the rest of them is roughly some kind of little interval here. Okay. So this value of delta I've drawn on the graph, f maps that interval of radius delta around A to this kind of two-component bit over here. There's a bit of it inside the epsilon interval, but there's this bit of it which lies outside the epsilon. So this delta clearly does not work, okay? Because it's not true that if x is within a distance delta of A, then f of x is within a distance epsilon of A. Because if you choose an x slightly to the left of A, it will always be out here. And no matter how small you make the delta, that effect will always be there. No matter how small you make delta, there will always be an x less than array satisfying x minus a less than delta. Just take something slightly to the left of a, and this value f of x will be down near the point, near this point here, this down near the value you are. Okay? Which is outside the epsilon interval.
I was just wondering, obviously, if you were to determine whether a function was continuous or discontinuous, would you not need to look between an interval? Because obviously you could pick a point A on that discontinuous function where it would.
Oh yeah.
So does there need to be an interval that you between between A and B is continuous, but between B and C?
Oh yeah. So this function, as it suggested, at this point here, it's continuous. In fact, at all the points we can see on this graph, it is continuous, except for A. Yeah. So the definition we've given so far is a definition for a function being continuous at a particular point, not an entire. But if we then say just a continuous function, what we're really saying, it's continuous everywhere. So it's continuous at all. So the definition is a pointwise definition. It's a definition for what's happening at a particular point. And then if you just loosely say, oh, the function is continuous, I think what most of the time when people say that, they're implying that it's just shorthand for saying it's continuous. Yeah. Now the for all epsilon bit is important because there are values of epsilon for which we don't see the definition breaking down. If we had chosen an extremely large value of epsilon, epsilon very large here, to enclose the point 1, to include the point 1, then we would not see the definition break down. We would be able to choose a delta that worked. So if I make my epsilon interval very big so that the interval stretches down and includes the point y, then a very small delta will work, won't it? If I had included my epsilon interval to be down here, my epsilon interval around A, if it enclosed the point y, then yeah, a small value of delta would work. It would satisfy the implications between the inequalities. If you're close enough to A, the value f of x will be within this interval. That doesn't mean it's continuous because the definition says this, you have to be able to find the delta for every epsilon. So the fact you might be able to find the deltas for some value of epsilons is not good enough. You have to be able to find that value of delta for every value of epsilon. The definition says you have to do this have to be able to do this for every positive epsilon. That's the key point. Okay, the other queries. So this is a detailed enough formal definition that we'll be able to build arguments on. And we'll be able to see how the various operations on functions preserve this notion of continuity. Now there's various details of these proofs in the notes. And there's a second exercise, a second tutorial question about the sum of two functions. So as an example argument, so as an example of the application of this, we'll prove that the product function f of g is continuous at A if f and g are. So if f and g are continuous at A, we're going to now show that the product function f times g. So this is an example of the application of this. An example of the kind of arguments that we use. You'll spot many similarities to the proof of the product form of the algebraic limits theorem for sequences. Okay, the definitions are similar, and the proof arguments we build on them are similar too. Not exactly the same because we're in a different context. We're talking about functions, okay, and continuity at a different point in the domain, not sequences converging to limits as the index goes to infinity. But you still spot many similarities between the two. Okay. So we assume f and g are continuous at A. So I can make use of the formal definition of continuity for both of these functions. So now I want to try and prove that the product function f times g is continuous at A. So what we need to do is we need to control the size of the absolute value, or which absolute value? We need to be able to control the size of the absolute value of fg evaluated at x minus product fg evaluated at x. Because that's the one that features, in the definition of continuity. And make it less than epsilon. That's our goal. It's a task. How can we do it? Well, we do it using our assumption. The assumption tells us that we can control the similar absolute value when it's just f on its own, f of x minus f. Assume that's continuous. We can also control the size of the absolute value g of x minus g of a, because we've assumed that that's continuous. That's it. But now we need to be able to control this new absolute value. So the method, the technique, is to express the thing we want to control, to express it in terms of the things we can. So if we can find a precise description of this absolute value in terms, or as a combination, some suitable combination of the things that we can control, then we can use our control over those components to exert control over this. But we want to make this small. We want to arrange that this absolute value is smaller than epsilon. So we need to work on it, okay? So this absolute value, well, first of all, we can apply the definition of what the product function is. And that's good because now we see the appearance of the quantities f of x and g of x on their own, and f of a and g of a on their own. They're at least present in the expression. And they're multiplying here a function, but at least they're there. And then, yeah, so we make a bold kind of move. We attempt to say that this is, well, it's got to kind of depend on the product of these two. F of x minus f of a multiplied by g of x minus g of a. Yeah. If I can finish that equation, the equation is not true yet. But if you do multiply together those brackets, you get some elements of that expression there. You do get the f of x, g of x. And you get kind of f of a, g of a, but you get it with the wrong sign. You get plus f of a, g of a. But we need a minus f of a, g of a. So straight away we fix that. We need to subtract 2 times f of a, g of a in order to get the right term there. And then we also get various cross terms. We get an f of x minus g of a and a minus f of a, g of x. So to correct for those, because those aren't present here, we need to add them on again. So we need plus f of x, g of a, and plus f of a, g of x. Now I can finally close that absolute value. Now the equation is true. The second thing is the same as the first. Now I've made it look way more complicated than it needs to be. I mean, it was this nice simple expression. We've complicated it. But we've complicated it for a reason. We've complicated it so that we can begin to see the influence of the factors that we can control. We can control f of x minus f. We can control g of x minus g. And with a little bit of manipulation, we can see these appearing here as well. F of x minus f of a, g of x minus g of a, leave that alone. And these things, you see, I've got 2 copies of minus f of a, g of a. So I pair one of them with this, and I'll see that as f of x minus f of a multiplied by g of a. I'll pair the other copy of minus f of a, g of a with this quantity down here. And it will be, get the signs right, it'll be minus f of a plus f of a into g of x minus g of a. those are my absolute values. Get close to the edge there. Small. You see what I'm doing all the time? Wherever I can, I'm drawing out one of the factors I can control. Bracket f of x minus f of a. The bracket g of x minus g of a. The bracket f of x minus f of a. The bracket g of x minus g of a. I'm able to control all of those. Now it's looking like, remember, it's not just the brackets I can control the absolute value of each of those differences. Okay? At the moment, it's just one giant absolute value, so I need to split it up into the combination of all of them. But that requires the application of the triangle inequality. When you have a sum of, see, I've got a sum of three quantities here. This thing plus this thing plus this thing. So I've got three numbers added together, and I'm taking their absolute value. Now, the individual numbers might be positive or negative. So the absolute value of the sum isn't necessarily the sum of the absolute values. But it is no bigger than the sum of the absolute values. So we can apply the triangle inequality to say this is the absolute value of f of x minus f of a multiplied by the absolute value g of x minus g of a plus absolute value of g of a times absolute value of f of x minus f of a, drop down to the next line, plus absolute value of f of a times absolute value of g of x minus g of a. That's by the triangle inequality. And properties of other properties of absolute value, that the absolute value of the product is the product of the absolute values. Rather than just writing the absolute value of all of this here, this first product term, I write it as the absolute value of this times the absolute value of this. Because that's true about absolute values. The absolute value of the product is the product of the absolute value. Finally, everything is exposed. Each of these absolute values I have control over because we've assumed the functions are continuous at a. This first absolute value can be made small. So can this one. This is just a fixed constant. It's the absolute value g of a, which is whatever it is. But it doesn't change. It's always its own value. But it's multiplying an absolute value I can control, and similarly for the last term here as well. So you can see what we do in the notes. Basically, what I want to do is I want to make, it's still the sum of three terms, this thing plus this thing plus this thing. I want to arrange that each of them is less than a third of epsilon. Then the whole thing will be less than epsilon. Three terms added together. The easiest way to do it is to arrange, call on the definition of convergence to arrange for me that each of these three terms is less than epsilon over 3. So we know that there exists a delta 1 such that if x is within a distance delta 1 of a, that's going to imply that absolute value of f of x minus f of a, and I can choose it to be as small as I want. Now, one of the things I'm going to choose it to be smaller than is the square root of epsilon over 3. And I'll do the same job for the g of x minus g of a, so that when they both get multiplied together, I get an epsilon over 3 in this first term. So I at least want this to be smaller than the square root of epsilon over 3. But I also want it to be slightly different, or to a slightly different description of how small it is for the second term. Because this second term, which is added here, I want this to be less than epsilon over 3. So to do that, I'll need this absolute value to be less than epsilon over 3 times the absolute value of g of a. And a neat way to arrange that it is smaller than both descriptions is just to require that it be smaller than the minimum of. Bit of a technique, a stylistic technique there, if you like. I require two different ways to describe the smallness of f of x minus f of a. On the one hand, I want it to be less than the square root of a third of epsilon, so that when I do the same thing for g of x minus g of a, that whole first term will be smaller than a third of epsilon. But to generate a third of epsilon in the second term, I need it to be smaller than epsilon over 3 multiplied by g of a, which will cancel out the g of a factor there. And I do exactly the same thing for the function g. I know it's continuous, so I know that there exists a delta 2, such that the absolute value of g of x minus g of a will have the required form, and it's just the corresponding thing, again, less than the square root of epsilon over 3, and also less than epsilon over 3 times the absolute value of f of a. You can see why it's f of a, because the factor f of a is the thing that's multiplying the absolute value. Now these smallness measures are reached at, under two different descriptions. One when x is close to a measured by delta 1, the other one when x is close to a measured by delta 2. And again, just a neat trick of tying it all up nicely to ensure that x is close enough to a to satisfy both of these. I just let my delta be the minimum of these two, delta 1 and delta 2. So if x minus a is less than delta, x is within a distance delta of a, I can immediately I can call upon these upper bounds for the absolute value. So we get that the absolute value of the product fgx minus fga, now all of these are strictly less than, so it's strictly less than, that's the thing at the top, fgx minus fga. We went through all this manipulation and it's less than or equal to this last line. But now I'm going to replace all the parts of it by strict upper bounds. So that less than or equal becomes a strictly less than. And it's the square root of epsilon over 3 times the square root of epsilon over 3 plus absolute value g of a. So this absolute value g of a is that factor there. But I replace the absolute value of f of x minus f of a with this upper bound. Epsilon over 3 times absolute value g of a. And I do a similar thing. Last term, I replace g of x minus g of a by this upper bound. Epsilon over 3 times absolute value of f of a. And that looks kind of horrible, except you notice it's all going to simplify because you get epsilon over 3 plus epsilon over 3 plus epsilon. So that upper bound there is exactly epsilon. And just in those 3 lines there at the bottom, that is the definition of convergence for the product function f. The epsilon, I didn't place any restrictions on the epsilon. So this epsilon could be any positive number. That wasn't restricted at all. We used the definitions of continuity for f and g to get useful upper bounds that made it so that this difference, the difference in value of the product function at x to the product function at a, such that that is strictly less than epsilon whenever x is within a distance delta. So this proves, therefore, fg is continuous at a. So that's an application of our formal definition of continuity to the application to the problem of proving that the product function is continuous if its factors are continuous. So this places us in a good position to begin the study of differentiation next week, I think. For the tutorials this week, I think if you look at questions 1 and 2, questions 1 and 2 on the end of end of chapter exercises, page 69, questions 1 and 2 for working with tutorials this week. Okay, thank you all for listening.